welcome to Elizabeth Tech's PhD Defense. As usual, the process is going to be roughly a 45-minute talk, followed by an open question session for a few minutes, and followed by a closed session with the committee, at which point we'll ask everyone except for the committee to leave. The committee is myself, Xiao Zhu, Rachel Ryan, and Jacob Bay, all here. Okay, good. This is the important thing. I have to check that everybody's here. All right, now so Alyssa has been with us for about 6 years. She got her undergrad degree at Macalester, and she's been working with my group since arriving here on this cloud, the BRIC, where she's been doing a deep study of the molecular spectrum in this particular cloud. She's also had a big contribution to the department in other ways. She's been a huge supporter of the Retro project, and she supported a lot of the outreach and teaching to pre-collegiate students in the department. So she's played a big role in that regard. But today, what you're going to hear from her is about the research she's been doing as part of my group. And so, Alyssa, please go ahead and take it away.
Thank you. Oh my gosh. Thank you. Thanks, Adam, for the introduction. Hopefully everybody can see me with the sunlight. When I was practicing, it was nighttime and it was like pitch black in this room. It's a lot better now though. Okay. Let's see if this does anything. Click once. All right. Yeah, so that was my title slide. Adam did a great job of introducing me. Basically, I chose this title, Star Formation in a, quote, extreme environment, to contrast with if you were at Nazar's PhD defense. The object that he studies is a lot more extreme than the object that I study. So that's why I put it in quotes. But the BRIC is still extreme, and you will find out why in this talk. Because this is a long talk, I would like to start by giving an outline of the topics that I'm going to cover. I'll start by going over some background information, setting the scene for the current state of what we know about star formation in the Milky Way's galactic center. So yeah, I study star formation. I'm an observational astronomer, so I'm going to talk about how we observe star formation. And then I'm going to talk about the main project that constitutes my dissertation, which is called the BRIC Line Survey. It's an observational project with the ALMA telescope. I'm going to talk about the setup of the survey and the process of doing the data reduction for it, as well as results of the survey and implications of those results. I'll finish by talking about a bonus paper that I got using the survey data, which is about this molecule methanol undergoing this strange non-thermal process. And I'll conclude finally by addressing remaining open questions in the field of star formation and how my project either does or does not contribute to answering those questions. Without further ado, okay, I'd like to start by showing you the Milky Way galaxy. This is the slide everybody picks to show what the Milky Way looks like, because since we're in the Milky Way, we can't really take a top-down picture of it. So this is an artist's rendition of what we think the Milky Way looks like from above. Some features that I'd like to point out are that the Milky Way has spiral arms. There's actually multiple sets of spiral arms sort of in between one another. And there's also the central region where the spiral arms meet. It's not a single point, but instead it's this barred region. You are here. This is the solar neighborhood. Solar neighborhood is kind of the 500 parsec radius circle around the sun. Yeah, most of the stars in the constellations that you see when you look up at night are like from this region. A lot of local star formation regions are in the solar neighborhood. The reason I point out the solar neighborhood is to contrast it with another region in the galaxy called the galactic center. That's what I study. And so the galactic center, the exact definition of it is sort of depends on what field, like subfield of star formation or really galactic astronomy you're talking about. But in particular, here is a like schematic view of the what we think the structure of the galactic center is. These are all top-down pictures of this central barred region. So yeah, we can see some features of this barred region. There's these dust lanes that lead into the center that extend from the spiral arms. There's these like individual labeled clouds, and there's also this section in the center labeled CMZ. I will define what CMZ is on the next slide, but as a spoiler, it stands for Central Molecular Zone. And on the right-hand panel of this plot, we zoom in and look at 3 potential geometries for this CMZ region. The exact structure is like debated because we can't see, the CMZ from the top down. We kind of have to infer the 3D geometry of it, you know, what's in front of what, using data. So basically, these are 3 hypotheses for what the structure is of the CMZ. Oh yeah, and I labeled the CMZ here. I forgot I did that. Okay, so as an observational astronomer, when we observe the galactic center, like I said, we can't look at it top down. Instead, we're looking at it through the plane of the galaxy. And when we do that, we're looking through a lot of material. This is a visible light photo taken with actually an amateur telescope in visible light, which shows us sort of the conditions that we see when we look towards the galactic center. So some features of that are an extremely high stellar density. All this like white fuzzy stuff, these are individual stars. And another feature that you can see are these very dark dust lanes. Those are dust that is obscuring light that might that we know exists because we know that the stars extend into the central region. But that's not all. We know there's stars, there's dust, but there is also gas that penetrates these regions where stars are forming, where these stars come from. And so there's both atomic and molecular gas that's in this region. And I zoom in on this inset area. This is the actual center of the galaxy, gravitational center. And this is a picture of gas in that region. I'm going to blow it up even more. Because this region contains a lot of molecular gas, and as star formation people, the field calls, well, molecular gas is very important, and I'll talk about why. We call this region, for that reason, the central molecular zone. So this is a multicolor image of this region where each of the colors corresponds to a different species of molecular gas. This is from the ACES collaboration. So in summary, a lot is going on at the galactic center between like all the stars that are there, all the gas and the dust that's coming from the spiral arms accreting onto this central gravitational potential. And one thing that I didn't mention is that right in this bright region to the lower right, there is a 4 million solar mass supermassive black hole hanging out inside there, Sagittarius A star. So yeah, it's a busy area. It stands to reason that perhaps the physical properties of that region are distinct from those in the solar neighborhood. Things might be denser, they might be hotter, they might be more kinematically complicated. It turns out that this is exactly true. So this is a table comparing, I blatantly stole this from Czar's defense because it's just a very useful summary paper, comparing basically physical quantities in the CMZ with other regions. We have the solar neighborhood, we have CMZs in other galaxies, and we have high redshift galaxies. I'm going to point out a few of these quantities, starting with gas mass surface density, which is basically how dense is the gas. The CMZ is at least an order of magnitude, if not more, dense than the solar neighborhood. Gas and dust temperatures are also several factors, like factor of 2 or 3 higher in the CMZ than in the solar neighborhood. And I'm also going to point out this parameter called line width, which is essentially a proxy for how turbulent is the material in a region. We see that the CMZ is like 4 times more turbulent than the solar neighborhood. And something else I can point out is that the conditions in the CMZ are more similar to the conditions of extragalactic CMZs in general, as well as high redshift galaxies, than they are to the solar neighborhood. So all of these like different parameters in these different regions, the reason that we care about that is because we suspect that these parameters can affect the way that stars form in the region. Okay, so I study star formation. I should probably talk about how a star forms. Here is a simplified view of star formation. We start with a loose collection of gas and dust, a cloud. The cloud undergoes gravity. Gravity begins to pull the material in the cloud together, and the cloud begins to collapse. As the cloud gets denser and denser, any initial angular momentum that the cloud had will start the cloud spinning, like an ice skater bringing in their arms to do a really fast spin. Eventually, you get very high pressure or a very high density in the center of the cloud. And that high density and high pressure from the density can ignite the fusion of two hydrogen atoms into a helium atom. Or that there's some other things that go on, but basically that ignition means that a star has formed. Eventually you have the star with the conservation of angular momentum material around it in a disk. And then eventually that can evolve into a planetary system. So that's the very basic and incorrect view of how stars form. This is a more complicated version, which is taken from the Starford simulations. I'll start the video now. What the simulation shows and why I chose it to demonstrate star formation is that clouds do not collapse monolithically, one cloud into one star. Basically, you have a single cloud that can undergo fragmentation, collapse into individual smaller cores rather than just like one big thing. And another thing that picture doesn't show is right now, you see these points have these jets of material being shot out from them. Those are outflows from young protostars, basically feeding back material into the natal cloud that they come from. And that feedback can affect star formation. It can trigger star formation. It can also suppress star formation, depending on what was going on. If there was a dense region that got blown apart by an outflow, that might affect the way that a star might form in that particular area. Okay, I will cut the simulation short because it's just the same thing but rotating. Okay, so there are some ways that we can characterize the CMZ that relate specifically to the way that stars form there. Here are two different measurements that do that. On the left-hand side, we're plotting the star formation rate of a cloud, a given region. Some examples: Milky Way clouds, starbursting galaxies, high redshift galaxies. The CMZ is on here too. We're plotting the star formation rate in that region against the amount of gas that's in that region. On the right-hand side, we're also plotting star formation rate, but instead of just gas, we are only looking for dense gas. So the very densest parts of these clouds, we're counting up the amount of gas in those regions. So we see that in general, there are some trends. The more gas you have, the more gas you have, the more stars you're going to form. The Milky Way generally agrees with this idea. It's, within it, the error bars of many other points. Unfortunately, if you consider just the dense gas, if you normalize against this like linear fit, we can see that the CMZ is performing between 10 to 100 times worse. It is producing between 10 to 100 times fewer stars for the reservoir of dense gas that it has. So we know that stars are not forming the same in the CMZ as they are in these other regions. Otherwise, it would be forming more stars. Okay, so basically we want to figure out how different properties in the galactic center can affect the way that stars form there. That is an open question in star formation. However, a problem is that many of the properties of the galactic center make it difficult to study star formation there. Basically, in regions where stars are being born and they're embedded, and also they're very distant, like the CMZ, individual protostellar anatomies are difficult to interpret and also find. But something that we do know is that stars form where there is dense gas. And to look for dense gas, we tend to use different tracer molecules. Those tracer molecules would be a molecule that is present only where the molecular gas density is above a certain amount, because in lower densities, they would get destroyed. N2H plus on the lower part of this plot is a great example of a dense gas tracer, because right at about 10 to the 22 molecular hydrogen particles per centimeter squared, at densities below that, this molecule, N2H plus, cannot exist. It will be dissociated by a process that I don't exactly remember. But basically, it is correlated with densities over this amount, 10 to the 22. So that's great and cool. But an unfortunate thing is that in the CMZ, the average density is higher than this amount. So this tracer is great at differentiating between gas on either side of this boundary, but what it tells us in the CMZ is that the gas is dense, and we knew that already. So this can also be extended to tracers for other non-star formation related conditions like shocked gas, for instance. If you're looking for high velocity gas and you're using a shock tracer like SIO to look for it, in the CMZ, a tracer like SIO traces even relatively low velocity gas, because a lot of the gas in the CMZ is moving at generally high velocities. So that's a problem, but it is a problem that we can solve. All right. I would like to introduce to you a molecular cloud that is going to solve this problem. That cloud is called the brick. Hooray. The brick is, okay, I'll show you where it is. And this is another view, multi-wavelength view of the central molecular zone. The brick is a cloud that's at the beginning of this series of clouds called the dust ridge that starts with the brick and ends with Sagittarius B2, another common topic of study in the Ginsburg group. And until the 2020s, the brick was thought to generally be not forming any stars. It was thought that this cloud is quite quiescent, it's very dense, it's very cold, and it's not forming many stars. Because of the qualities of this cloud, thanks, I'm really proud of this. Because of the qualities of this cloud, it was hypothesized that maybe the brick is a precursor to the formation of a massive star cluster, several of which exist elsewhere in the CMZ, like the arches and quintuplet clusters. Maybe it's just that, but hasn't formed all its stars yet. Low resolution observations of the brick discovered a few tentative signs of star formation in one particular region of the cloud, circled by this white circle here. Basically, they found a water maser, that's these pluses, that was coincident with dust continuum emission, this pink and blue stuff, well, more the pink stuff. And, that correlation means, okay, maybe there is, a star forming in that core. Because there's a water maser at that location, this area was deemed the maser core. So yeah, these are the low resolution observations, but follow-up high resolution observations of specifically that maser core and the surrounding region revealed that there is cloud fragmentation in this region. There is internal heating in the cores here. And they also found bipolar outflows from several protostars in the region, which is unambiguous evidence that, yes, there is definitely star formation happening in the brick, at least in this region. Okay, here are those high resolution observations, not my data, presented in Walker et al. 2021. First, let's look at dust in the cloud. So these are the high resolution dust continuum observations of this circular region. Some things that I like to point out are, so the central core, what we thought was maybe just a single core, it turns out is actually two distinct lobes when you look at high resolution. And we also see a lot of lower mass cores that are in this region that we totally didn't pick up at all in the low resolution data. If we move on from looking at the dust to instead looking at outflows using the molecular SIO as a tracer, we see that there are lots of bipolar outflows from these cores. That's illustrated by the blue versus the red on either side of the core. This one also looks like it extends in a long jet. There's definitely some outflowing happening by the central core, although it seems like it might be complicated, especially because there's maybe two cores there. So that's cool. There's outflows. That means star formation is happening. Bringing in another molecule, which is 13CO. CO is the most abundant molecule in the ISM besides molecular hydrogen, H2. This 13CO is very complicated. These are different velocity slices through this region. And as you can see, we're not moving very much in velocity. I know you can't see these numbers, but it's like maybe 4 km/s chunks. The velocity, the structure of the cloud as you step through in velocity is drastically different as you go. One important feature that I like to point out that we can see in the 13CO high-res data is this sort of bilobed cavity, the axis of symmetry of which is this dotted line you can sort of see. We think that this is associated with the outflow from that central core, or one of the outflows from that central core. So yeah, there's this bilobed cavity-like structure. There's another sort of hourglass feature around another core that you can sort of see here, this core number 8. It's got this like hourglass shape around it. Kind of looks like the Pearl Jam album cover that I don't remember the name of. So yeah, that's cool and great. We didn't know that that was there until we had these observations. But you may be thinking, if you're thinking ahead, Alyssa, there is a problem. The CMZ, whoa, I mean, the brick is in the CMZ. Does that not mean that it will fall victim to the same problems that all the clouds in the CMZ have, where the dense gas tracers don't trace dense gas and the outflow tracers don't trace outflows and shock tracers don't trace shocks? I will say to that, that's a great concern, but due to the brick's relative quiescence compared to, other regions like Sagittarius B2, we know that there are SIO outflows that are traced by SIO. So that's good. However, the brick is still indeed representative of the CMZ region because of how dense it is and because of how kinematically complicated it is. It's just less so than more complicated regions in the CMZ. So that makes it a great thing to study for a PhD thesis. Before I go into that, I'm going to do one of two slide asides, which is a term that I made up, to give some background information on observational astronomy for people who may not be astronomers in the audience, which is only people online, basically. So I'm an observational astronomer. As we could see in those initial visible light images of the CMZ and the galactic center region, there's a lot of dust towards the galactic center that obscures visible light from getting to our eyes. That means if we want to observe what's going on at the galactic center, we cannot use visible wavelengths. We either have to look at very high energies like gamma rays or high energy X-rays, or we could go to lower wavelengths like in the microwave or the radio or the infrared regime. I choose to look in the microwave or submillimeter regime because a lot of molecular gas, which is the type of gas we're trying to study, when it's heated, emits spectral lines in that regime, in that region, in the submillimeter. So that's what I look at. That motivates this project. I do so using this beautiful telescope called the Atacama Large Millimeter / Submillimeter Array. It is a telescope that is made up of 66 individual antennas that are sitting on a plateau that's 16,000 feet above sea level on a mountain in Chile, where there's less atmosphere to go through, which is important for submillimeter observations. ALMA is an interferometer. Each of these antennas are tied together using a very powerful computer called a correlator, which, as its name implies, correlates the signal between all the antennas to give us an idea of, like, a picture of what we can see on the sky in submillimeter light. And all of these antennas working together give ALMA the resolving power of a much, much larger telescope than any of the individual antennas. Each of these antennas is equipped with like 9 now receivers that cover basically a great portion of the submillimeter spectrum. And I use 3 of the receivers on each of these antennas. Okay, so enter a survey that is dedicated to using the brick as a template for finding tracer molecules that are appropriate for locating star formation in extreme environments like the CMZ. So yeah, this is the survey that my thesis is based on. The real goal of it is to find tracers that differentiate star formation related processes like proto and prestellar cores and their outflows, differentiating those from things that are unassociated with star formation, like shocked gas or just like loose diffuse gas that there's no cores in. This is a very wideband survey. It covers like 90 gigahertz of frequency coverage with ALMA. And this GIF at the right shows, basically it demonstrates our resolution. So we can see we are working at a lower resolution than Dan Walker's data, but we can still see there's a central core. We don't resolve it into 2 individual objects. And there's these, like off-center cores as well as some like loose diffuse gas that we can see in the continuum at 90 gigahertz. So yeah, the goal of the survey is to develop a list of tracers that can be used to interpret existing shorter or smaller bandwidth surveys of both the galactic center and also extragalactic CMZs, where these tracers might be useful. Okay, first step of the project is to define regions that we want to differentiate between. So we've chosen to do that, this central core region, and we're contrasting it with this region of diffuse gas off to the lower right. the name of this region that we have chosen is the frown. That is due to a paper, the other paper that I will talk about later. It looks like that. It also looks like ditto. That's why I put ditto. Okay, so I'll explain that later. Well, I'll explain the nomenclature later. But basically, in the survey, we detect emission lines from many, many molecules. Here is just one that I've chosen. This is the molecule methanol, a particular emission line. And in the survey, we basically focus on rotational excitation of these molecules, as opposed to vibrational or row vibrational or any of the other weird modes. Sorry, they're not weird. Any of the other modes that molecules can vibrate, move in. Okay. Another quick 2-slide aside on atomic and molecular spectroscopy and energy levels. Atoms have energy levels that are quantized. If you impart energy to an atom in a specific amount, at the exact right amount, the atom, or really its electron, will jump into an excited energy state. Because nature abhors things that are in excited states, the atom is going to want to jump down into a less excited state. And when it does so, it emits a photon of a specific energy that's related to the difference in energy between the state it jumped from and the state it jumps to. So a given atom is only going to emit photons of specific energies or frequencies, which gives a given atom a unique spectral fingerprint, which is very useful for identifying an atom, light from an atom. The same thing is true for molecules, except that molecules have a lot of atoms that make them up, as well as bonds between the atoms. So their energy level diagrams are way more complicated. This is the energy level diagram for the molecule methanol. Regardless, we know that photons or collisions can bump particles, whether they are atoms or molecules, into and out of different energy states. And that will create light when the particle becomes de-excited. So that light, you know spectra from prisms and, you know, the gas lamp experiments that you do in like early physics classes. This is a submillimeter spectrum. So seen with a submillimeter telescope, many of these lines are from the molecule methanol that I just showed. So all these little lines, there's one over here and one over here as well. This is an example spectra. This is a lot of the data that I work with. This is what it looks like. Okay, so what I did in the survey was extracted spectra from that core region and from that frown region across our entire survey bandwidth, which is shown here at the bottom of the screen. This plot summarizes the number of molecular lines that are detected across the bandwidth, each in 1 gigahertz wide bins. So this is for the top bar, the number of spectral lines per bin in the core, same for the frown, and this is noise information on the bottom. One thing we can infer from this plot is we can see that there are more lines at higher frequencies detected in the core than there are in the frown. This implies that the core is an area of higher excitation than the frown. There are more lines or more molecules that are in higher excited states than there are in the frown, pardon me. So, oh wow, that looks weird. So basically what I did was I performed LTE modeling for both the core and the frown on those spectra for 176 twiggle molecules. It's something like that. I cut off some ones in these plots that they don't matter as much. But yeah, we found that basically there are like 70 detections either in the core or the frown amongst the molecules that we surveyed. The detections are these solid bars. I know this is totally unreadable, but it's just in a summary view. What I'm plotting here, so in fitting these spectra, there are different knobs that you can tune. You can fix the velocity of the material to adjust the position of where the lines appear along the frequency axis. The important knobs are rotational temperature, which is related to the excitation of the molecule, and also column density, basically how much of that molecule is there per unit area on the sky. And the column density is what we're displaying here on the y-axis. So these are sorted by the core column density and the frown column density. For molecules that we don't detect, we measured upper limit column densities, basically how much of that material could be there without us detecting it. So, ta-da! The process of actually fitting the spectra, I would like to demonstrate so that it is more clear. Basically, what I did was extract for any given molecule. This example one is HC5N. I would go through, see from a database where all the spectral lines are expected to be, plot them, and then generate a model based on some parameters for rotational temperature and column density. And then I fit the model to the data kind of by eye, which sounds miserable, and it was tough, but you can get initial guesses for the rotational temperature and column density parameters by using this one neat trick astronomers won't tell you about, which is rotational diagram analysis. For molecules that have rotational modes, what you can do is use your spectra. For each of the lines that you detect, you add up the integrated intensity of the line, basically the area under the curve, and you plot that area, basically, against the upper state energy of that transition that creates that line. So basically, what is the energy of the upper state? And if you plot that, Mangum and Shirley found out that if you fit a line to those points, the slope of the line is related to the rotational temperature of the molecule, and the y-intercept is related to the column density. And that's like of the material that created the spectrum. So that's awesome. And that gives us initial guesses for doing this modeling. And they're pretty good guesses for some molecules. For some, they're less informative, but it's a great tool that I used for all of the molecules that I detected. Okay, I am right on time. There are some molecules that we detect in both the core and the frown. These are those molecules. This doesn't directly answer the question of like what lines and species trace which regions, but the really important thing about these molecules is that having them detected in both places allows for measurements of the conditions in each region that are not biased by, one being from one molecule versus another. An example molecule here, this is CH3CN or methyl cyanide. Methyl cyanide is a thermometer molecule that essentially has all of its spectral lines very close together in these things called ladders. And the relative heights of the lines in the ladder are very sensitive to the temperature, like the rotational temperature of the molecule. So you can get a very precise temperature estimate from this methyl cyanide molecule. And it's great that we detect it in both places because we can get, a nice measurement of the temperature in both regions. So that's good. There are some molecules that we find that are unique to the core. Here are those molecules. They are HDCO, which is deuterated formaldehyde, DNC, which is HNC with a deuterium instead of a hydrogen, one complex organic molecule, C2H5CN or ethyl cyanide, and also deuterated ammonia as well. So these are things we do not see in the frown. These are moment maps. Something else is probably happening with HDCO. There's a little bit of emission off center, but for the rest of these, they're in the core and they're not really in the diffuse gas around it. So that's great. These might be core tracers. In contrast, there are a lot more molecules that are in the frown, but not in the core. However, for some of these molecules, we measure an upper limit column density in the core. That is, when you normalize to the column density of methanol in that region. We use methanol because it's an abundant complex organic molecule located in both regions, and it's good to normalize to that. So those upper limits are sort of on the same order of magnitude as the column densities that we measure in the frown. So there's a lot of those molecules that, a lot of those molecules that could be there without us seeing it. But there are some molecules where, there's almost a 1-dex difference in the core to, frown to core column density is a plural. And these are some of those. And I've shown a selection of different moment maps from some of these molecules, all of the ones with arrows and also an extra one, 13C methanol. So these are all things that look like they're tracing diffuse gas, maybe even tracing the edge of that outflow cavity that we saw in Dan's high resolution data, or at least one side of it is particularly lit up. And yeah, so so there was a lot of deuterated molecules in the core. There's much more of a range of molecules that seem to be unique to the frown. We have 15C variants of HCN, a couple different 13C variants of HC3N, which is another, I don't know if it's 1, 2, 3, 4. It's not a complex organic molecule. It doesn't have enough atoms. We also have some shorter molecules like SIS. And 13C methanol as well is not in the core. So the main deliverable from the project are these lists, as well as that entire catalog of the upper limits for the molecules we don't detect, as well as inferences that we can derive from those measurements. And now I would like to talk about those. Okay, so this is a list of all the complex molecules that we detect. Why do we care about complex molecules? They're biological precursors. They tend to form in areas where stars are forming. And it's really useful if you measure COM abundances in one region, you can compare them to another region, and that can probably tell you stuff. I'm not familiar with every COM, but some of them I am. So basically what we did was compare relative column densities for complex organics in the brick, core, and frown to those same COMs in other regions where stars are forming, both in CMZ and beyond the CMZ. So the green and cyan points here are from Sagittarius B2 Deep South, which is a slightly different area than Nizar works on, but it's still in a more prolific area of star formation than the brick. We've got also some cores. The grayscale ones are from Sag B2N, which is where Nizar studies. But there's also one region that is not in the galactic center, and that's W51. There's one core from W51 that we compare here. In general, this is a very busy plot, but generally when a COM is detected in the core or the frown or both, the abundance or the column densities of that COM are basically quite similar to the densities that we see in these other regions when you normalize them to the methanol column density in that region. The one difference here, which I forgot to point out with an arrow, but it's CH3CHO. This is the molecule acetaldehyde. It appears to be slightly underabundant in these Sagittarius B2N cores and more abundant by like an order of magnitude in the brick core. So that's possibly significant. It could be, I'm not sure what could be causing that, but it is possibly significant. Another area that this survey provides insight into is how chemical reactions are proceeding in the brick, either in the core or the frown. The chemistry of a region both depends on and dictates the abundances of different species that end up being present and detectable in the region. So chemistry is important to look into. So I looked into two different ratios that I will present to you today. One is the 32S to 34S isotope ratio. So this is two different isotopes of sulfur. There was a survey from 1996, Chen et al., that found that there tends to be a decrease in this ratio as you move towards the galactic center. But the region that they studied was only between a galactocentric distance of between 5.5 and 7 kiloparsecs. So that's closer to the galactic center than the sun, but it doesn't get anywhere close to reaching and probing the galactic center. There was a follow-up to this in 2020, Humeyer et al., which tried to extend this measurement to the galactic center, in particular two clouds, the 50 kilometer per second cloud and Sag B2N. They used the molecule CS to measure this ratio, and they found it to be like 18 or so. Versus the Chen et al. Prediction was that the ratio would decrease to like 4 or less or more in the galactic center. So they found something that is in strong conflict with that. In our data, we can measure this for another location in the galactic center and see if we get something that matches. Unfortunately, we can't use the same molecules that Humeyer et al. Use because we think that the molecules are subthermally excited, which basically means when we do LTE modeling, it's not very accurate. We'd have to do non-LTE special modeling to figure out what the actual conditions are that could be causing the spectra. So basically, instead, we use a different molecule, SO. And we can only measure this for the frown because that's the only place that we have a great measurement. And we can basically measure the ratio. We get like 8 plus or minus 8, which is not in conflict with this 18. It's also not in conflict with the 4. So basically, maybe the brick has a lower 34S abundance than other CMZ clouds, but also maybe it's an agreement. Sometimes chemistry is hard. Another ratio that we can measure, this one is more definitive, is the C to O ratio, the ratio of how much carbon to oxygen there is in a region. The reason that we care about the C to O ratio is that it affects chemistry a lot. It decides what the dominant molecule is in a region, whether it's H2O or CO. And both of these atomic abundances and the ratio have galactic gradients that have been measured. So there's a recent paper that was just published in February that used chemical network modeling to investigate the relationship between a ratio of this type of molecule that I don't know how to pronounce, but it's basically HC3N, 5, 7, etc., where they're odd numbers. The ratio of that to H2CO, formaldehyde. So yeah, the relationship between that ratio and the C to O ratio of a region. So they basically did independent modeling and measured this empirical, I think empirical is the right word, this empirical relation. So there is a slight problem in our data that formaldehyde has some unsplit hyperfine lines in the frown. So the fit we get is not great, but we can still get a decent estimate of the ratio between HC3N and H2CO. But we get about 4.6. We also detect HC5N. Again, these are both in the frown. The core is a little messed up. But the ratio of HC5N to formaldehyde is about 1.1 plus or minus 0.7. So if we look for those ratios, the HC3N is the red line, HC5N is the blue line. They kind of, by the time you get to relatively low fractions of that molecule to formaldehyde, you're sort of in the same regime of C to O ratios. Basically around 1.1 to 1.2, which are within 1 sigma of each other when you consider these errors. So we know that in the frown, the C to O ratio is about 1. That's great. That's awesome. Okay. So yeah, those are the big takeaways and deliverables from the Brookline survey. Now I'm going to spend the next like 4 minutes talking about the side project that I did first, using the Brookline survey data. I would like to begin by asking, who knows what a laser is? Hopefully everyone, because I have one right here. What if I told you you could have a laser, but in the microwave? It is called a maser. The way that masers and lasers are generated is you basically have this situation called population inversion. You have some pumping mechanism that takes a population of particles and brings them preferentially into an excited state. And then you have some stimulated, like a photon that stimulates the emission of a photon, bringing the particles down into a lower state, creating a laser or maser. There's obviously some geometry involved because these are very linear. It's a linear emission process. And there also needs to be a source of coherent amplification. Well, that's the coherence, but the amplification, there needs to be some pumping mechanism that's causing that population to be bumped up. Something strange is that you could have the same thing, but the other way around. It's called a DASAR, which is a bad acronym because there's no amplification and it's not stimulated, but basically you've got a situation where there's a particle, molecule in this case, that is getting pumped preferentially into the lower state of some two-state setup. And when you measure the ratio between the number of particles in the upper state versus the lower state, you can measure this excitation temperature. This is related to which energies or which temperatures of photons that that molecule can absorb. So then in this case, because we're in a lower state, the particle would absorb a photon and go back up into its excited state. Because it's weird, it's non-thermal, it's like, nothing's moving between the states. Well, There might be some amount of that, but mostly things are moving down into the lower state. So yeah, this actually happens to a lot of molecules: formaldehyde, cyclic C3H2, and even the molecule methanol. Except we didn't know when we started this that this could happen to methanol at this particular frequency. Basically, we were going through making moment maps of all of the methanol lines in the Brick line survey. We saw one that was in absorption instead of emission, and the absorption and the emission were very spatially correlated. So we said that's kind of weird. One cool thing about this, these like energy, like the number of particles in the different states, if you finesse the level populations enough that you can get the excitation temperature low enough, if TEX is below 2.73 Kelvin, you can make the particle absorb CMB radiation, which is normally not possible because this is the backlight of the universe. These photons are coming from every direction. And so mostly things are heated by that. But in this case, this material could absorb that light. But okay, spatial correlation isn't enough. What if it's just a coincidence? We did non-LCE modeling of this region and of this line of methanol, and basically figured out that for values that make sense of the densities and column densities that might be present in the brick, we do get this absorption. The absorption is real. I will zoom through the rest of this because I want to get to my final slide. But basically, these quasars are really cool because you can use them as a redshift independent way to measure the conditions in different galaxies, because of this cool thing called the angular size redshift relation. If you want me to explain it, ask me later, but it's not that important. But yeah, it's very neat. This has been demonstrated for other molecules, but the great thing about this line of methanol is that for high redshift galaxies, it will be redshifted into an observable range for the next generation of radio telescopes, like the NGVLA. So that's great. And those telescopes are not optimized for the frequencies of more common quasars. Okay, I said I would end with discussing open questions in galactic center star formation, and now I'm going to do that. So I'm going to start with a couple questions that are probably not so open at this point. How do stars form in the galactic center? It appears that they form similarly to how they form elsewhere. There's cores, there's outflows. That's cool. But why is star formation in the galactic center different than in the galactic disk? Well, we know that the conditions in the galactic center are extreme. Things are very dense, things are quite turbulent. This appears to disrupt star formation, reduce the amount of stars that are being formed for the amount of dense gas that's there. What are the initial conditions for star formation in the galactic center? A way that the Brick line survey can help answer this is that we probe regions of density and column density that we can compare to other regions in the CMC and see, what are the lowest densities where we're still seeing stars able to form. And also, stuff that we haven't explored in the data, we haven't really looked at those off-center cores. If there's a star forming in there, that might be at a different density that we can, use to make more constraints on what conditions permit star formation. So there are some questions that my project can sort of more directly help answer, such as what role do chemistry, turbulence, and gas kinematics play in galactic center star formation? Well, as I showed, we can and have measured isotopic and elemental ratios in at least the Frown. I would be interested in looking into more ratios in the core, particularly because there's all those deuterated molecules in that region. I think deuterium chemistry is interesting, and all I know about it is that it's cold. It needs to be cold for things with deuterium to form. And so that might also be an interesting thing to study in the core. We haven't really explored that. We also really haven't explored turbulence and gas kinematics, but we do have shocked gas traced by traditional shocked gas tracers in the data, which we haven't yet extracted a spectrum from, like that region, but that's a natural extension of this project. Oh, spoilers. Okay, why is the brick forming so few stars? There are many possible explanations for this that have been presented in previous papers. Maybe the brick is still young. Maybe the brick has not undergone some triggering star formation event where there's like some cloud-cloud collision that causes a burst of star formation through the cloud. These data do not inform those hypotheses, really. There are data that our research group has that do, like the James Webb data that you saw on the first slide. But the Brickline survey does tell us that the brick is turbulent. And perhaps that is suppressing star formation, like it appears to be in the bulk of the CMZ. The most direct question that the survey was designed to answer is which lines trace what physical processes in the galactic center. And as I've shown, we've made significant strides towards identifying species that trace protostellar cores and species that trace non-star forming associated gas that's more diffuse. So we know that that's true for the brick, and now we can test it elsewhere in the galactic center by looking for these species. And I guess I'll leave this up. This is my last slide. I don't have any pictures. So thank you so much, and I'm willing to take questions now.
A few questions from the general audience. Start with Chris.
It was a handful of slides back, but you were basically showing us a bunch of different molecules of interest. And I noticed that many of them have deuterium. Why? Yeah, this and the previous two that you showed. Is deuterium just like a useful thing because it has like distinct lines, or why is it why do so many of these molecules like deuterium?
That's a good question. I have a couple answers that might get at answering the question. Basically, what I know about deuterium is that it needs the conditions where the molecule, so deuterium is heavy hydrogen with an extra neutron. In order for that to occur, the region must be very cold. The core, before, like as opposed to the frown, must have been quite cold before like the protostar started being a protostar there. And to me, that is like a natural reason why you would get this in the core and not the frown. The other thing is that in sort of a what are we sensitive to in the survey viewpoint, these deuterated versions of these more common species like HNC, the non-deuterated versions tend to be detected on a very widespread scale. Because this is an interferometric survey, we're not sensitive to things on very large scales. So we still detect these molecules, the non-deuterated versions. It's just harder to interpret their signal because we're missing the largest scale information because almost an interferometer. If we had single dish data, maybe that'd be a different story. But for now, these deuterated species are what we can't detect because they're less abundant on those large scales.
So this is a pretty exhaustive survey of one region.
Mm-hmm.
Is this enough? Like, do you never have to do this again, or is there value in doing this in other regions?
I personally think there is value in doing this in other regions, mostly because there are tools that we created from this that then can be used, and then nobody has to reinvent the wheel. But yeah, I think that if you have a situation where, like, for a cloud that's like the brick, where it's more easy to interpret than the rest of the CMZ, or if you have like an extragalactic, CMZ that you're looking at, or like some region in another galaxy, I know there are some wideband surveys of NGC 253, the Starburst galaxy, and I think it would be cool to look for maybe species like this there. You can't see individual cores and stuff, of course, but you can, maybe test things on like larger scales, like diffuse gas tracers. So yeah, I think it'd be worth it. Maybe I'm biased because I did all the work and I don't want to see it like just sit there. But yeah, thanks for the question.
Do you know that the brown is part of the CMZ?
Ooh, great question. How do we know that the brick is part of the CMZ? Well, the brown basically appears to be, well, it's at a velocity 12 kilometers per second. That's sort of at the same velocity as like other parts in this region. And as long as we assume that the brick is a cohesive cloud, which is not a given. One of the hypotheses is that the brick is actually like multiple clouds that are seen in projection along, like, along the line of sight. But at least in this region, it appears also this is just a morphological comparison, but it appears, especially because we see in 13 CO that large cavity, this, like the frown is tracing this sort of, maybe this edge of it. As long as the core is associated with the CMZ, well, that's not the core, but as long as the core in there is associated with the CMZ, it makes sense that the frown should too if they're associated physically, if that makes sense. But yeah, I can't speak to whether the brick is part of the CMC. I know there's been some drama about that recently.
All right, any more questions from the general audience?
Thank you for coming to my talk.
Oh, yeah, let's thank them.